Hi, I'm Jacob. I'm going to be talking about compile time contract checking and generally using C++'s type system to provide interesting guarantees, in this case around pointer nullability. So here's a little outline, background, what we did, how we did it, and then some of the lessons we've learned. So hi, I'm Jacob. I'm on the platforms and libraries team at Dropbox. I actually come from an embedded systems background. I've been at Dropbox since 2012, and that's pretty much when I started getting heavily into 2012, or heavily into C++, excuse me. I've been involved in most of our cross-platform mobile efforts, like Sync, data stores, more recently Carousel, and I'm also the maintainer of Genie, which we gave a talk on yesterday. So in the past, I've been deep down in the trenches of embedded systems and such, but more recently, moving into larger scale stuff. So some background, first of all, and motivation on what we're trying to do here. One of the interesting things about C++ is that there is a lot of flexibility in what your program means. So consider this line here, f open paren x plus y comma z. Well, what does that mean, right? So first of all, f could be a function with a bunch of overloads. It might be a template. We might be doing type deduction. Operator plus itself might be overloaded. We might be doing a complex addition or concatenating strings or something. Even more deeply, there might be ADL if f is not in this namespace. F might be a type, in which case this probably doesn't do what you wanted to do at all. It makes it temporary and throws it away. We've had bugs around that. Also, the parameter on the left is an R value, and the parameter on the right is an L value, which may also affect what gets called. So C++ is very customizable. And sometimes that's a curse. I've heard of people with C++ environments with rules like no templates. But that's basically throwing the baby out with the bathwater, right? You can do extremely powerful things to make your code cleaner and better and simpler by customizing what your types are and what exactly primitive operations on them do. And I think unique pointer and shared pointer are the best current example of that, right? When you have a shared pointer, and you copy it, you actually increment a ref count. And that's great. I've converted code that manually called incref and decref to use shared pointer. And it was amazing. It shrinks by like a third. And we find bugs that were there that we never noticed because if you pulled out the flash drive here, we never closed the yada yada. So you have this ability in C++ to customize what you can do and what you can't do also with unique pointer. You can't copy a unique pointer. You just can't. So, null. Well, null footer. It's a little bit easier to deal with now. There aren't quite as many horrible problems. But null sucks, and it can creep into your program in various ways. Can anyone tell me what is wrong with this line of code? Well,
the compiler can potentially assume that because you have this is not null, and it will
exactly.
Optimize it away.
Right? It's perfectly reasonable to write this, and your compiler will go, oh, well, this is always true, or converts to true, so I'm just going to get rid of it. It might warn you about the fact that it's removed a redundant comparison. And the problem is that by the time you're hoping that your assert this will trip, the world has already ended. Demons are already flying out of your nose. It's too late. It's just too late. And there's a similar problem with references. Usually references mean this isn't null, but if they are, then too bad. So null is a pain. We can use our type system to enforce contracts. And an example of a contract of unique pointer that we enforce with the type system is you can't copy this. You can only have one unique pointer that points to this thing. So we can use the type system to check our null as well. One of the principles that I've been trying to follow is we want to catch problems with code as early as possible, right? There's this whole sequence of things between when you write a line of code that doesn't work, or doesn't work sometimes, and when it actually blows up. The best thing is for, if you're using an IDE that does this, a little red squiggly line to show up. And the worst thing is it makes it to production and causes undefined behavior, and your name is in the news, or there's a CVE, or slightly less bad, you get a bunch of crash reports from your users. And so the faster you can catch things, the better. This is one of the key differences between what we're doing and the not null in GSL, as talked about Monday, Tuesday. We want to move this all the way forward. Not just a few steps, not just to asserts, not just to static analyzer, which maybe you run every time you build your program, but probably not. Let's put it in the type system, in the compiler. So enough about the problem that we're trying to solve, which is null happens and we don't want it to. Well, first of all, here's what we're not doing. We haven't built a non-nullable pointer that just asserts on dereference or on construction. That's pretty easy to track down. We can do better. We're also not interested in annotations, because an annotation that isn't part of the type system can very easily get lost. I've written this type a couple times, and it does not do what I want it to do. This is syntactically valid. It's fine. You can make a std function with a no except annotated function parameter. It has absolutely no effect. It's exactly the same type as std function void, because no except, one of its many problems, is that it's not actually part of the type. It's part of the type of a function. It's not part of the type of a function pointer. So for nullability, Clang added nullability annotations, mainly for Objective-C and Swift, and they're kind of nice. They will detect, hey, you're passing a literal null or nullptr to this function call. That's nice. But I can say whatever star x equals null, f of x. We can do better. So here's what we built. It's on GitHub. It is a wrapper type called nn, which is like t, and it behaves like t in as many ways as I could possibly get it to do so, except it can't be default constructed. The way you get an NNT is either by writing an explicit null check, and we have macros for that, that either assert or throw or take your pick, you can write your own, or by having something that's not null from the beginning. And we found when we started using this in our code base that a lot of times a given pointer, be it a member or something that's being passed, callbacks, etc., there's just no way that this ever could have been null. We don't ever come from a nullable pointer. So we have an nn make unique at the top. It threads all the way down through. The type is annotated everywhere. And it means that every time I write this type, I know what that annotation is. It's not null. An nn can implicitly or explicitly convert the underlying type. We can compare it, we can hash it, we can stream it to std if we want some debugging. And it also has both implicit and explicit constructors that match the implicit or explicitness of the type that wraps around it. So this is sort of a whirlwind tour of making a type that's almost like this other thing, except not quite. So here's the constructor of nn. We put in, so I promise I checked for null t is just an empty struct. It's a tag. The idea is you can't write this by accident. But we provide, you say, OK, I solemnly swear I checked this for null, and it's not null. Or I'm relying on the contract of make unique or such. And then we also have helpers, make unique, make shared, check assert, check throw, that do whatever check. And mostly we try to use nn make unique or nn make shared. We don't use the assert and throw things nearly as much as we thought we would. So let's say I have a function. It takes a non-null pointer. I have a nullable pointer. OK, well, I wish I didn't. But I can write that explicit nn assert, and the right thing will happen. This is actually a macro that expands to a lambda that has an assert inside it and then does a return. We also have a type converting constructor, which basically says nn behaves like the underlying type when passed a non-nullable version of the underlying type. This means that implicit upcasts, for example, work with both shared pointer and unique pointer, and also raw pointer. We also have an explicit constructor, which has to be enable if only if the other constructor isn't allowed. Otherwise, it would be ambiguous. And so this lets us take a non-null annotated raw pointer and explicitly hand that over to a unique pointer. We don't do that very often, but if you want to, you can. When trying to build this, the goal was completeness. And finally, there are all of the things that you can't do with a non-null pointer. For one thing, you can't convert it to bool, because if you think you want to do that, then you're confused. In our test harness, we actually wound up writing a truthy helper function that does return true for a non-null type and operator bool for a nullable type, because sometimes in generic code that's useful. More often than not, this helped us find dead code where we annotated something as non-null because we were pretty sure it was supposed to be non-null, and then found that someone, in some cases it was me, had written, just to be sure, if this is null, return null, or if this is null, throw some error. And deleting this operator bool let us, in the type system, find that dead code. Obviously, you can't construct this from a null pointer t. One nice thing is the compiler, if it finds an explicitly deleted constructor, and both GCC and clang do this, will print out the entire line containing that constructor. And so we have a comment at the end saying very specifically, you can't do this. Without that explicitly deleted constructor, this would behave exactly the same, but you would get a page of confusing, well, we couldn't find a constructor. These are all the ones we considered output. And then finally, a constructor from the nullable version of the type, and for an assignment operator from the nullable version of the type that says, hey, you might want to use one of these macros. We actually put the names of the macros in the comment, but that would run off the end of the slide. Past that, it just works. You have an implicit cast. We have an explicit as nullable operator, and you can use operator star, operator arrow. That just forwards on. So a non-nullable pointer behaves just like a nullable pointer in every way we could possibly think of. Shazam. OK, real life gets in the way. It actually doesn't just work. And we've run into a number of bugs in toolchains and compilers. First of all, CLion. I'm not trying to dunk on CLion here. Parsing C++ is really hard, but it got confused by what we did with decal type. It also got confused by trailing return type for some reason, so we wrote a little trait as a workaround. We wanted NN to work with raw pointers. This is not a non-nullable version of shared pointer. It's a non-nullable wrapper around whatever. I haven't tried it with std function, but it might work, or exception pointer. It might just work. So we wrote a trait to get the underlying thing. We also found a clang bug. If there are any clang people in the room, please fix this. It stinks. If you have a nullable shared pointer and you try to assign it from an R-value non-nullable pointer, clang can't decide whether it should implicitly convert to an R-value and then use the R-value constructor, or implicitly convert to an L-value and use the L-value constructor. I think this is a clang bug. GCC and MSVC disagree. But that's one of the reasons why we added the as nullable helper, was to have a workaround. It turned out there were a few other cases where, for clarity, it's really nice to be clear, this was non-nullable, but I'm taking the nullable version because I might want nulls later on. So I can write that in the code. So we added that, and things work better. And so we built this probably a year ago. We started incorporating it into the code base slowly, mostly because it was an experimental thing. We wanted to see if it actually, 1, helped, and 2, was usable. More recently, we added support to Genie, or CodeGen, so that the interfaces that it generates will also have annotations. And we found that it helps a lot. Every time we NN convert a swath of code, there's some little bug, or there's some little piece of dead code that can't actually have been there. There's some place that would have maybe probably been caught by the assert this that doesn't actually work. We had to do some restructuring. There are bits of the C++ standard library that very deeply assume that anything can be default constructed. Usually that's a good thing. This kind of messes with it. Unfortunately, most things do have a sensible default constructor, right? It makes sense to default construct a string. You get an empty string. It makes sense to default construct a map. You get an empty map. Std map and std unordered map, square bracket operator, require that your thing be default constructible. Nothing else in map does. But if you want to use square bracket, It will construct it if it's not already there. So we did have a few places where we had maps from something to non-nullable pointer, and that was fine. We just changed them to not use operator square bracket equals and instead do in place or whatever else. The other interesting interaction is with move semantics. There is, as far as I can tell, still debate over what exactly are you allowed to do with a move from object, right? Should it be wrong to touch it at all? Should it be well defined? And that really doesn't work with non-null. So yes, the emperor has no clothes. A non-null pointer is null if it's been moved from. I think this is a case that sort of shows that moved from objects should be considered dangerous. You can't do anything with them. We should have robust tooling around that. I would love it if all the major compilers yelled loudly if I tried to use a moved from object, maybe someday. That would help. That would make me feel much better about having this there. Right now, it's a hole. But I think that's resolvable if we have, this is sort of the one place where this does depend on static checking until we can get in the language some sort of move from detection, which probably isn't going to happen. Std move is dangerous. Oh well. And then finally, integration. So we work across 3 different languages, C++, Objective-C, Java. Objective-C and Java have had some level of null annotation for quite some time. It's advisory. Java has, last I looked, 3 or 4 different sets of annotations that you get to pick from. Standards, that's the wonderful thing. So Genie, if you're familiar with it, generates code based on an IDL in C++, Java, Objective-C, now Python, and gives you translation between them. So we spit out the nullability annotations for an interface, whether it's optional or not. There is some future stuff that we found that we would really like to be able to do. The biggest one is implicit casting, and I was relieved to see that this is a problem that GSL's nonnull hasn't solved either. Right now, we can't just say, please replace all of the make shared in your code with nn make shared. Because if you have, for example, a function that returns a base, returns a pointer to a base, and at the very end you write return make shared of derived, whatever, then that works great. There's an implicit cast from shared pointer to derived up to shared pointer to base. But if we replace that with nn make shared, then you will get an nn shared pointer to derived, or an nn of shared pointer to derived, which could implicitly cast to a nullable shared pointer to derived, or a non-nullable shared pointer to base, but you don't get 2 implicit casts in one, so it fails. I've started working on this. I think it's also blocked by the same compiler bug, because it involves a very scary implicit conversion operator, convert to t, if t has these properties on it. So maybe someday. And then the other future direction that we might be able to go with this is integrating with, or overlapping with, or interacting with static analysis tools like GSL. The question is, can there be common ground here? So that's what I've got. Next up, any questions?
Yeah, so you just mentioned GSL. That's a question I've had throughout your talk. How this is
Yep.
different from non-null?
Yeah, so not null is implicitly constructible from a nullable pointer, and our nn is not. You have to actually write out, we can go back to the example slide. Basically what we do is require that you be explicit about your boundaries between this is a nullable thing, and after this point it can't be null. With GSL, that's written down in the type, but it's not written down at the call site, which has its pluses and minuses. I think it's probably easier to adopt GSL's not null because you can do it piecemeal much more easily. It's much more like a precondition check than a type change. And so here, by putting it in the type, we make it so that you have to express this nullability guarantee all the way through. You don't magically go from one to the other. That's the main difference.
The prevailing sentiment I've heard about move from objects is that they should maintain all of the invariants of the type that they were originally.
Yep.
Why did you decide to violate that invariant in your move operator?
So we don't really have an option. If we could make if we didn't violate that invariant, we could still work with shared pointer. There would be an efficiency hit because we would have to keep the reference until the moved from thing disappears. Unique pointer would be hopeless. So it's a trade-off between making this usable versus keeping the invariant for a situation that hopefully won't arise.
And what would you want to see in this move from analysis?
So the analysis I want to see is there ever any code path wherein an object can be move constructed from, which is sort of subtle because the move from is actually some other constructor taking it as an R value. So the semantics would have to be boiled down clearly, but can an object be modified in some way by the assumption that it's moved from? And at any point after that, do we do anything to that object except for destruct it or assign to it? So that's sort of a data flow thing. I haven't put enough thought into it to know precisely what the rules would have to be, but it seems pretty doable. Yeah?
Did that C-line bug you found also exist in CDT, or did you check?
I don't know. The workaround is not that bad, so we just did it and moved on.
Which compiler is optimizing also this? Which one did you check?
We've checked GCC and Clang. We mostly use GCC and Clang, and I've done some looks at the generated code because so this nn check assert, it is a lambda that we construct and then immediately call, so it's all very local and goes away. I haven't looked at whether what MSVC produces for this or any other compilers. I know MSVC is happy to compile it, but I haven't confirmed that it optimizes away.
How easy was it for the rest of your team members to adopt to this? And how prevalent is it throughout your code base now?
So it got a lot more prevalent sort of overnight when we landed the Genie change. That was the hardest part. Before that, it was a slow growth. People picked it up. People liked having the extra guarantee and the extra safety. But adding it to an existing code base, it's the sort of thing that happens slowly. But it was not that, there were no big fights over whether we should do it or not. It was just sort of a slow, hey, let's write this. But the Genie change let us and required us to do a simultaneous refactor of all of our implementations of Genie classes. That was tricky. That was the biggest driver in me wanting to have an implicit upcast from NN derived to nullable base. Because if I do that, then we could just change all of the make uniques to NN make uniques, and a lot of code wouldn't have to change. Cool. So that's all.